Beneath the Taklamakan Desert, Chinese engineers drilled past rock that is 500 million years old and found oil. That alone should have rewritten the geology textbooks. But that discovery is almost a footnote compared to what else came back up. There was water where water cannot exist. There were rock formations that behaved like liquid under pressure. There were core samples so scientifically significant that China's own researchers compared them to lunar soil material, so rare and so irreplaceable that scientists treat individual centimeters of it like artifacts from another world. And when the results came in from the deepest borehole ever drilled on Asian soil, a 10,910-meter hole punched straight down through 12 layers of geological history, the full data was not published, just quietly absorbed into state energy programs and academic reports that most of the world will never read. This is the story of what happens when you drill 6.7 miles straight down into the earth. What you find there, and why the people who found it aren't entirely sure the old rules of geology apply anymore. But to understand what China actually discovered, you first have to understand why this kind of drilling is so difficult that most countries gave up trying, and why the ones who kept going found things that nobody expected. The Tarim Basin is one of the strangest geological environments on Earth. It is the largest landlocked basin in China, roughly the size of California. The Taklamakan Desert sits inside it like a dried sea, and in geological terms, that is almost exactly what it was. What is now desert was once covered by ocean. The sediment from that ancient ocean settled and compressed over hundreds of millions of years, and as the tectonic plates shifted and the Tian Shan and Kunlun mountain ranges rose up on either side, all of that compressed sediment got pushed deeper and deeper underground, deeper than almost anywhere else on the planet. Which means that if you want to know what the Earth looked like 500 million years ago, if you want a direct physical sample of rock from that era, this is one of the few places on Earth where you can reach it by drilling. The question is whether you can actually reach it at all. Nobody had ever done it before. Not in Asia. Not on land. The deepest borehole ever drilled in human history, the Kola Superdeep borehole in Russia, reached 12,262 meters, and it nearly broke the Soviet Union trying. That project, started in 1970 and abandoned in 1994, remains the deepest hole ever dug on Earth. The Americans had their own attempt. Project Mohole, launched in the early 1960s, tried to drill through the oceanic crust to reach the mantle directly. It got far enough to prove the concept was possible before Congress cancelled the funding in 1966, spooked by the cost and complexity. Both programs produced extraordinary science. Both programs also demonstrated something that engineers had not fully appreciated going in. That the deeper you drill, the less the physics resemble anything you have dealt with before. The way metals fatigue, the way fluids move, everything changes. China knew this. They drilled into it anyway. The Shenditake 1, well, the name translates loosely to Deep Earth Exploration, began drilling on May 30, 2023. It was located in Shaya County in the Aksu prefecture of Xinjiang, inside the heart of the Taklamakan Desert. The nearest city of any size was Kola, and from there the drilling platform was a long drive across flat, featureless desert where summer temperatures regularly exceed 40 degrees Celsius and the sand gets into everything. The platform itself was built around the world's first 12,000-meter automated drilling rig, a machine developed entirely within China specifically for this project. More than 90% of the components in the drilling system were domestically designed and manufactured. This was not a joint venture with Western technology. This was China, alone, deciding it was going to drill deeper than anyone on its continent had ever drilled, and building what it needed to do it. The first 1,000 meters took 4 days. That pace would not last. In the early phases of drilling, progress is relatively straightforward. The rock is younger, softer, and more predictable. The team moved through it quickly, reaching 5,856 meters by late July 2023, less than 2 months into the project. By October, they were at 8,000 meters. By Christmas, they had passed 9,000. It took 279 days to drill the first 10,000 meters. That was, by any measure, the fastest onshore drilling to that depth in history. It set a world record before the well was even finished. And then the last kilometer nearly broke them. The final 910 meters from 10,000 to 10,910 meters took more than 300 days. More than half the total project time was spent on less than 10% of the total depth. Every additional meter, as the platform director Min Peng put it, increased drilling complexity exponentially. That is not a figure of speech. It is an accurate description of what happens to the physics of drilling when you push past 10,000 meters on land. The temperature at that depth exceeds 210 degrees Celsius. That is hot enough to vaporize cooking oil. The pressure exceeds 145 megapascals, greater than the crushing force found at the deepest point of the Mariana Trench. The combination of heat and pressure does things to rock that are difficult to convey without experiencing them. Rock at that depth does not behave like rock at the surface. Under sufficient heat and pressure, rock flows. Slowly, almost imperceptibly, but it flows. The borehole walls don't just sit there while you drill. They push back, they squeeze, they close in. What was open when you drilled it may not be open when you pull the drill back up. And the equipment wasn't built for any of this, because nothing had been built for this before. Conventional drilling tools and sensors began to fail. The extreme hardness of the formation's rock that had been compressed for hundreds of millions of years under the weight of mountains wore equipment down faster than any model had predicted. The drill pipe weakened. The load on the pipe reached 665 tons. That is not the weight of the rock being drilled. That is the weight of the drill string itself, the kilometers of pipe hanging in the hole, exerting force on every joint and coupling. The technical team described the situation as overloading, wellbore instability, drill fatigue, tool failure, and severe formation loss all simultaneously. Lead technician Wen Liang said it plainly. They overcame a series of technical difficulties that had never been faced before, including extreme loads, wellbore instability, and formation leakage. He did not say they had expected to overcome them. He said they did. And then they found something that had no right to be there. At a depth of between 10,851 and 10,910 meters within the final 60 meters of the hole, the sensors detected oil and gas. Active, living hydrocarbons present in rock formations that are at least 500 million years old, under conditions that traditional geological theory said should make oil and gas storage impossible. According to the prevailing models, at those depths, and in rock that ancient, there should be no reservoir space. The pressure and heat should have destroyed any hydrocarbons that ever formed there. The pore structure in rock that old and that compressed should be too tight to hold anything. The physics simply should not allow it. The physics allowed it. Wang Chunsheng, chief expert of the Tarim oil field and the well manager on Shenditake 1, stated directly, "This marks the first discovery of oil and gas beneath 10,000 meters on land globally." He was not speaking loosely. No one, anywhere in the world, had ever found oil on land at that depth before. The discovery didn't just expand the map of where oil might exist, it contradicted the theoretical framework that the map was built on. CAS academician Hao Fang explained what this means in plain terms. According to traditional theory, in very deep and very old strata, there is no reservoir space, and oil and gas cannot exist stably. The discovery of oil and gas in a 10,000-meter well proves the opposite. It doesn't just challenge one assumption, it challenges the entire model of deep earth hydrocarbon behavior that has guided oil exploration for a century. But the oil was almost not the point. The core samples were, when you drill a borehole at this depth for scientific purposes, you don't just drill. You extract physical cylinders of rock cores from each formation you pass through. These cores are irreplaceable. They are the only direct physical evidence of what the Earth looked like at that depth, at that geological age, under those exact conditions. You cannot simulate them. You cannot recreate them. Once the borehole is sealed, that rock is unreachable again, possibly forever. Every centimeter of core is a primary source document for the history of the Earth. The Shenditake-1 project retrieved the first core samples in China and in Asia from a depth exceeding 10,000 meters. The cores reach back 540 million years into geological history. Scientists examining them described their significance as comparable to lunar soil. That comparison is not hyperbole. Lunar soil samples are considered among the most scientifically valuable materials ever collected. They are stored in climate-controlled vaults, handled with instruments, and rationed out to research teams in milligram quantities. The comparison suggests that what came up from those cores is being treated with the same level of scientific reverence. Using those cores, along with logging data and rock cuttings from across all 12 geological formations, Chinese researchers created Asia's first 10,000-meter geological profile, a comprehensive stratigraphic record of what lies beneath the Tarim Basin from the surface down to 500 million years ago. Nothing like it had existed before for this region. And given the geological uniqueness of the Tarim Basin, the way it was formed, the depth of its sedimentary record, the way the surrounding mountain ranges compressed and preserved it, that profile contains information about Earth's history that cannot be found anywhere else. The scale of what was drilled through requires a moment to absorb. The well penetrated 12 geological formations. Each formation is a distinct layer of rock deposited under different conditions, at a different time, composed of different materials. Moving through them is like reading pages of a book, except the pages are hundreds of meters thick, and the ink is mineral composition, fossil content, pressure history, and chemical signature. The formation at the bottom, the one that contains the oil, is more than 500 million years old. That predates complex animal life on Earth. The Cambrian explosion, the moment in evolutionary history when multicellular organisms began diversifying rapidly into the body plans we still see today, was happening roughly at the time that rock was being deposited. You drilled to the Cambrian, and you found oil there. Nobody had ever done that before. Now, here is the part that makes engineers nervous. It took humans 300 years of drilling history to drill only 0.2% of the way to the Earth's core. 3 centuries, 0.2%. The Shenditake-1 well is the second deepest vertical borehole ever drilled. It is still, in planetary terms, barely a scratch. The crust beneath the Tarim Basin is estimated to be around 40 to 50 kilometers thick. This well reached just under 11 kilometers of that, about a quarter of the way through the crust. The mantle, the layer of partially molten rock where the real strangeness begins, is still 30 kilometers below where the drill stopped, and the conditions at that point already exceeded the crushing pressure of the Mariana Trench. The question that Chinese engineers are now asking is not whether they can go deeper. The question is what they will find when they do. Sun Jin-sheng, an academician of the Chinese Academy of Engineering, put the challenge in perspective. At depths surpassing 10,000 meters, a series of extremes relentlessly tests the boundaries of ultra-deep drilling technologies. He compared it directly to the difficulty of lunar exploration programs. The comparison is apt. Drilling to the moon requires solving problems of vacuum, radiation, distance, and precision. Drilling to 10,000 meters on land requires solving problems of heat, pressure, rock behavior, equipment failure, and geological unpredictability, often all at the same time, with no ability to retrieve the equipment or diagnose the problem from a distance. The world's first 12,000-meter automated drilling rig, developed entirely within China for this project, was the technological breakthrough that made Shenditake-1 possible. The rig is designed to operate at depths up to 12,000 meters, which means there is already a plan, or at minimum, a capability, to go further. Not today, not immediately. But the infrastructure exists. The technology has been tested under the most extreme conditions available on this planet's surface, and the results came back positive. What the rig found in those final 60 meters changed the economics of deep Earth energy exploration in ways that are still being calculated. The Tarim Basin contains vast reserves of oil and gas, and it has been one of China's most important energy regions for decades. But the accessible reserves, the ones at moderate depths, reachable with conventional technology, are being depleted. More than 80% of the basin's deep oil resources and nearly 64% of its deep natural gas are buried below 6,000 meters. By the standard definition used in the industry, any well deeper than 6,000 meters is classified as an ultra-deep well. China has drilled more than 300 such wells in the Tarim Basin alone. They account for more than 80% of all ultra-deep wells drilled in the country. The discovery of hydrocarbons at 10,000 meters does not just represent one well. It represents the potential unlocking of an entirely new tier of the basin's resources. If oil and gas can exist stably at that depth, if the geological models that said it couldn't are simply wrong, then the reserve estimates for the entire Tarim Basin need to be revised, significantly upward. Wang Qinghua, executive director of the Tarim oil field, stated that the discovery has laid the foundation for the strategic discovery of deep oil and gas exploration. That is carefully chosen language. Strategic discovery means this is not a one-time find. It is a proof of concept for a new category of resource. And that is before you consider what the discovery implies for every other deep sedimentary basin on Earth. Because the Tarim Basin is not unique in having ancient, compressed sedimentary rock at extreme depths. Similar geological structures exist in Russia, in North Africa, in the deep portions of the North American Craton. If the old model was wrong about hydrocarbons at 10,000 meters in the Tarim Basin, it may be wrong elsewhere too. The implications for global energy reserves are not small, they are potentially enormous. And they are currently sitting, largely unexamined, in Chinese state research reports and CNPC internal data. Which brings us back to the classification question. The full scientific dataset from Shenditake-1 has not been published in the way that scientific discoveries typically are. There have been press releases. There have been official announcements. There has been a carefully managed stream of information describing records broken, technologies developed, and broad categories of discovery made. But the core sample analysis, the detailed geochemical data, the stratigraphic profile, the specifics of what the hydrocarbon indicators looked like and at what precise depths has not been released in accessible form. The geological profile described as Asia's first 10,000-meter stratigraphic record exists. Chinese scientists have compiled it. It has been described in general terms, but it has not been shared. This is not unusual for a state-owned energy company protecting commercially sensitive information. CNPC is not a university research program with an obligation to publish. It is China's largest oil and gas producer, operating under national energy security directives that go back to explicit instructions from President Xi Jinping on deep Earth exploration and energy security. The project was described in official documents as a landmark project for building a national, strategic, scientific, and technological force. Strategic, scientific, and technological, all at once. What that means, in practical terms, is that the discovery belongs to China, not to the scientific community, not to the world's geologists who might want to revise their models based on what was found, to China, as an asset, as a state resource, as a piece of the energy security infrastructure that the country has been systematically building for 2 decades. And this is where the story becomes something larger than a drilling record. China's investment in ultra-deep drilling did not begin with Shenditake-1. By the end of 2024, the company had drilled 191 wells in the Tarim Basin at depths of 8,000 meters or more. The progression of that depth record tells a story of its own. It took 29 years to advance drilling depth from 7,000 meters to 8,000 meters in the basin. The jump from 8,000 to 9,000 meters took 15 years. The jump from 9,000 meters to beyond 10,000 meters took only 3 years. That is not just technological progress, that is acceleration. The curve is getting steeper. The timeline is compressing. Whatever is happening in the deep geology of the Tarim Basin, China is learning it faster now than at any previous point in history. The implication is not subtle. The country that masters ultra-deep drilling does not just get access to new energy resources. It gets access to a new understanding of the Earth's interior, of how rock behaves under extreme conditions, of how heat flows through the crust, of how ancient geological events shaped the resource distribution of the modern world. That knowledge is not just scientifically valuable, it is strategically valuable in a world where energy independence is one of the defining variables of national power. Sun Jinsheng's comparison of deep drilling to lunar exploration programs was not accidental. He was describing something that is both a scientific endeavor and a geopolitical statement. China landed on the far side of the moon. China sent a rover to Mars. And now, China has drilled to 10,910 meters on land, the second deepest borehole in human history. He who reaches the deep sea exploration frontier, the deep space exploration frontier, and the deep earth exploration frontier simultaneously is not simply doing science. He is demonstrating capability, systematically, deliberately, in domains where capability translates directly into access and leverage. The Kola Superdeep Borehole, the Soviet project that still holds the depth record, was drilled during a period of Cold War competition, when every scientific milestone carried geopolitical weight. It started as an attempt to study the Earth's crust and ended as something else, a record that the Soviet Union could point to as evidence of what it could do. When it was drilled, the Soviet scientists found things that surprised them. They found water at depths where water should not have been able to exist. Water that had been forced deep into the rock under pressure, migrating down through microscopic fractures over millions of years. They found rocks that behaved like plastic. They found temperature gradients that exceeded all predictions. The Earth, it turned out, was stranger than anyone had modeled. The Shenditake-1 well found oil at depths where oil should not be able to exist. The pattern is consistent. The deeper you go, the more the Earth violates your expectations. The question of why this keeps happening has a theoretical answer, but the answer is unsatisfying. The models are built on observations from shallower depths, extrapolated into regimes that have never been directly sampled. Every assumption in those models about how pressure changes with depth, about how temperature affects rock permeability, about what conditions allow hydrocarbons to form and remain stable, was built without data from 10,000 meters. The data simply didn't exist. And now that it does, it is being absorbed, interpreted, and in at least one important case withheld. There is a version of this story where the classification of the results is entirely mundane. A state energy company drills a commercially significant well, finds commercially valuable hydrocarbons, and protects that information as proprietary. Nothing conspiratorial, nothing sinister. Just normal industrial secrecy applied to an extraordinary discovery. That version is probably correct. The oil and gas implications alone justify controlling the information, because publishing detailed data about the depth and composition of the hydrocarbon reservoirs would amount to handing competitors a roadmap. But there is another version, which does not contradict the first, where some portion of what came up in those core samples genuinely confounded the scientists analyzing them. Where the water that shouldn't be there, the formations that behaved in ways the models didn't predict, the evidence of ancient geological events that rewrites the basin's history, where all of that is being held close, not just because it is commercially sensitive, but because the scientific community is not yet sure what to make of it. Both versions can be true simultaneously. What is certain is this: the core samples retrieved from Shenditake-1 are being described by the scientists who retrieved them as having the scientific value of lunar soil. The geological profile they enabled is described as the first of its kind in Asia. The oil discovery they confirmed is described as the first of its kind in the world. And the full dataset from which all of those descriptions derive has not been made public. The comparison to lunar soil is worth sitting with for a moment. When the Apollo missions returned with samples, scientists spent years analyzing them. Some of those analyses are still ongoing. The samples revealed things about the moon's formation and the early solar system that no telescope observation had even hinted at. They were irreplaceable. They were treated accordingly. The researchers who had access to them understood that they were holding something that no one else could hold, something that could not be recreated, something that carried information about events that happened before the Earth itself was fully formed. The Shenditake-1 core samples reach back 540 million years. That is the Cambrian. Before fish, before insects, before anything with a skeleton or a nervous system had properly gotten started. The rock at the bottom of that well was being deposited while the first complex animals were slowly learning how to be complex animals. And that rock, those layers of ancient compressed sediment, contain a chemical record of everything that happened in that part of the world across those 540 million years. Temperature changes. Sea level changes. Chemical composition of the ancient oceans. Tectonic events. The slow geological processes that eventually converted ancient organic matter into the hydrocarbons found at the very bottom of the hole. The scientists who analyzed those cores are sitting on a record of 500 million years of Earth history, from one of the most geologically distinctive basins on the planet, retrieved through the most technically demanding drilling project Asia has ever undertaken, and they are not sharing it. He Jiangchuan, Vice President of PetroChina, described the success in terms that captured both the technical and the symbolic dimensions of the achievement. The success of drilling beyond 10,000 meters is another significant breakthrough for China following its advancements in space and deep-sea exploration. Space, deep sea, deep Earth. That is the trifecta. 3 frontiers. 3 domains where the physics become extreme, the engineering becomes impossible, and access to what lies beyond requires building capabilities that most countries cannot build. China has now planted flags in all 3. The rig that made it possible, the world's first 12,000-meter automated drilling rig, does not stop at 10,910 meters. It was designed for 12,000. The gap between where the drill stopped and where the rig is rated to go is more than a kilometer. The question of whether Shenditake-1 is the end of this story or the beginning of the next chapter has an obvious answer. Shenditake-1 set 5 engineering records. The world's deepest liner cementing, the world's deepest cable imaging logging, the fastest onshore drilling, exceeding 10,000 meters, Asia's deepest vertical well, and Asia's deepest onshore core sampling. Those are not just records for their own sake. Each one represents a technical capability that did not exist before. Liner cementing at that depth means you can stabilize a borehole at depths where the walls would otherwise collapse under their own pressure. Cable imaging logging at that depth means you can see, in real time, what the rock around your borehole looks like, what structures and formations you are passing through, what anomalies you should stop and investigate. The infrastructure of deep Earth science, not just the record, was being built in real time. The team that drilled Shenditake-1 involved tens of thousands of people across domestic and foreign enterprises, research institutions, and universities, 9 technical support teams, 10 new technologies developed specifically for the project. The world's first automated rig of its class, operated remotely from a control center in downtown Korla, hundreds of kilometers away. None of this existed before they needed it. All of it exists now. The question that sits at the center of this story, the one that the title implied and the data keeps circling around, is not really about classification or secrecy. It is about what the Earth actually is, at those depths, under those conditions. Because the honest answer is that we don't fully know. The models say one thing, the data keeps saying another. The Soviet borehole said another. The Shenditake-1 well said another. Every time humans have drilled deep enough to actually test the assumptions that the models are built on, the models have turned out to be incomplete. The Earth has a crust. Beneath the crust is the mantle, a layer of rock so hot and under so much pressure that it behaves like an extremely slow-moving fluid. Below the mantle is the outer core, which is liquid iron and nickel. And at the very center is the inner core, a solid ball of iron roughly the size of the moon. That is the model. That is what every geology student learns. And at the shallow levels where we can actually observe it, it is accurate. But shallow in this context means the first few kilometers, the first skin, the first fraction of a percent of the journey to the center. Everything below that is inference. Everything below that is model. Everything below that is extrapolation from seismic data and laboratory experiments and theoretical physics, none of which has ever been directly verified by drilling, because drilling has never gone far enough to verify it. 300 years of drilling, 0.2% of the way to the core. That is where we are. Shenditake-1 pushed that fraction a little further. It went deeper than anything on this continent had gone before. It found oil where oil was not supposed to be. It retrieved rock from the Cambrian and brought it to the surface. It created the first 10,000-meter geological profile of the most important deep sedimentary basin in Asia. And then it handed all of that data to a state energy company that is under no obligation to share it. What was found in those final 60 meters in that thin band of ancient rock between 10,851 and 10,910 meters, where the drill finally stopped, will shape China's energy strategy for decades. The discovery of hydrocarbons at a depth that theory said was impossible does not just open new resource territory. It raises a question that every energy geologist on Earth is now quietly asking. If the models were wrong about the Tarim Basin, where else were they wrong? That question does not have an answer yet. Finding it will require more drilling, deeper drilling in different basins, under different geological conditions, through different formations. It will require the sharing of data that right now is being held close. It will require international scientific cooperation of a kind that geopolitics currently makes difficult. Or it will require that someone else builds their own 12,000-meter automated rig and drills their own hole. The Earth is full of things we do not understand, things that contradict the models, things that push the physics past what we thought was possible. Every time someone has gone deep enough to actually check, the ground has given up a surprise. Water that shouldn't be there, rock that flows, oil at 500 million years. And somewhere below 10,910 meters, deeper than any drill on this continent has ever reached, the Earth is holding the rest of its secrets. We'll get there, eventually.